Hey guys, this is a short overview of the 6 degree of freedom motion hardware and software. Just a quick run through the hardware. This is the AMC 1280 USB motion controller card with its extension board, which functions to control the variable frequency drive. And in this case I'm using the Hitachi WJ200 1.5 kilowatt drive for this 1.5 horsepower 3-phase motor that's being used with the gearbox. The system is set up so that it can control up to 6 motors, so you can have different platform configurations. In this case I'm just testing a single motor system in gearbox, so I'm using axis number 1. This happens to be the actual direction outputs, the power supply for the control to the variable frequency drive. This is the start and stop. This is a display on the controller, so you can see the progress. This can be turned on and off. And there's some other utility functions on this controller that help it do what it's supposed to do. These outputs here are for the Hall effect sensors, which are used for position control. So down to the gearbox, I'll point out a few things here. This gearbox is about, I don't know, 28 inches long. This is the 1.5 horsepower motor. It's an inverter duty motor, and it's connected via a nylon coupler into this Nord gearbox. The gearbox itself is rated at about 11,000 inch-pounds of torque at the output shaft with the 1.5 horsepower motor. It's a dual shaft arrangement on the gearbox. The shaft diameter here is 1.75 inches. This little sensor is the Hall effect sensor, and it's set up right now to essentially read the position of the shaft, and it feeds that information as a voltage back to the AMC 1280 card. On this side of the gearbox is a foam mock-up of the actual lever system, which would be used to actuate the push rods going up to the platform. Again, this is a 6 degree of freedom motion platform, so the actual unit here is just one of 6 systems within the motion platform. They're arranged in a circular pattern at a given radius, and they do the job of actuating the 6 different push rods, similar to what I had shown in the model video previously. This lever here is going to be made out of steel, 1-inch thick plate with a form factor that'll essentially mount on the platform. The distance from the center of the output shaft to the push rod point was 6 inches. That's the initial point where I'll start testing. Depending on the amount of torque available and the actuation movements I want, I might increase or decrease this distance, but the 6 inches is what I'm going to start with initially. That should give a throw for each motor of about 11 inches of vertical throw with its corresponding opposite side. So the degree of platform tilt will be on the order of about 12 degrees for the platform movement in various directions according to the motion cues that are applied. So basically this is a 3-phase motor, and it's grounded to the power source, and of course the 3-phase lines L1 through L3 going up to the variable frequency drive unit. This is kind of the business end of the WJ200. This is where the input to the unit comes where you can actually control the direction, start and stop, feed it the voltage so that it can know how fast it goes according to the program settings within the variable frequency drive unit. This is a little junction box I have set up. This will actually be a 60 amp contactor that will be energized remotely and be able to be actuated within the cockpit. This will end up being a small module about this size, and that will serve as a kill function as well as initially powering up the entire system. So basically that's it. There is another unit here I guess I should point out. This is the braking resistor. This is 100 ohm 300 watts, which is compatible with this particular variable frequency drive unit, and it serves to help pull the energy out of the motor during a deceleration so that it can stop within a given period of time. Parameters I have set currently for this are 0.5 seconds deceleration ramp and then 1.25 seconds acceleration, and so that seems to be working out fairly well. The 24 volt power supply is a little switching unit that provides the milliamps necessary to feed this controller what it needs, and all of that gets tied into the flight simulator via the USB port. Okay, power is from a 50 amp 240 volt source, single phase, going into this system. Again, this is the contactor, manually controlled right now, but I'll replace that with the 240 volt contactor. The variable frequency drive, the VFD, activates, and so essentially right now this is connected to Flight Simulator via the software, and so it is essentially driving the motion system now. So in reality, I think this would be a procedure-oriented system where this needs to be controlled and activated and launched, so to speak, from the flight deck itself. Since this is a hobby kind of system, extra precautions need to be taken for single-use operation. There are no staff around here to kill things and reset things. So you're by yourself in the cockpit sometimes, and you need precautionary procedures and the capability to shut things down. So various ways to do that, as I mentioned. One is the cutting primary power. That shuts everything down. There's also input to the VFD itself that can be used to essentially kill all the motor functions at the VFD. There's the kill switch on the AMC 1280, and then of course there's the hold function and kill function within the motion software itself. So this system is actually activated right now, and of course the lever is not doing anything because the aircraft is on the ramp. It's cold and dark, and essentially nothing's happening. So I'll go ahead and start the aircraft, and then we'll do a taxi and takeoff. You can see this lever. As I mentioned before in other posts, I've got my simulator kind of in component modules right now. So this is sort of an example of what it looks like all torn apart. Anyway, this was important for me to test this unit out before I actually assembled the flight deck. And now I've got a pretty good idea of how this unit will behave, so I can start planning on the next phase of testing that will allow me to determine exactly how the flight deck ought to be structured. Okay, so I have Microsoft Flight Simulator running. I'm on the stretched screen here with NVIDIA Surround. This is running on the FSX computer. Again, the flight model, 737 flight model, is SimAvionics running on its own computer. This is the BFF 6 degree of freedom motion software. And right now it's in it's been started. The cue parameters have been set. It's sitting in a hold position. If I click on the drive, then the motion cues go into effect. It initializes all the parameters, and you can see it starting to get set up here. Once it finishes with that, it indicates driving, in which case it actually is sending out information to the variable frequency drive unit via the AMC 1280 motion controller hardware. One thing this allows you to do is fine-tune the motion cues. And for example, I can click on pitch here, and it brings up a variety of motion cue settings where you can set the actual scaling factors for various acceleration modes. You can actually change the acceleration parameters themselves. There are a myriad of combinations here that I'm learning, frankly, but I do have it set now with the aid of BFF to get I think a fairly realistic set of parameters that work with the 737 flight model. So again, the 737 is not a aerobatic aircraft and like an extra 300 or something, so all of these factors need to be adjusted accordingly to get the actual levers on the motor gearbox to move up and down at a rate that's compatible with what the software is doing in the flight model. So you can change these settings and for different areas. Pitch, roll, heave, yaw, and so on. All of these functions can be set via the keyboard in Flight Simulator, so I can use a keyboard control when Flight Simulator is active to put the system in a hold or a driving mode or actually kill it. So that's one area of control directly from the cockpit via the keyboard. So here I am sitting at Austria, where am I at? Innsbruck, Austria. And I'll go ahead and get this thing fired up, and then you can see the lever move a little bit.
On runway 26.
So we're lined up, ready for takeoff. This is the takeoff roll and initial climb out.
Positive rate.
Gear up. Coming up on a heading change. Rolling out on course. Notice the washout component. Okay, the Microsoft Flight Simulator weather weather is set for major thunderstorms. The drive is re-engaged. And you can see this is one of 6 axes, all going a fairly strong movement up and down. A lot of turbulence in this. Actually, I think excessive for such a flight deck, but in any case, this gives you an idea of some of the extreme ranges and also the acceleration, deceleration, forward, reverse movements that would be matched with the 737 flight deck. Under these conditions, this would be quite a ride in the cockpit. Coming up on a change of heading to the left. I think this is axis number 2, so in which case the lever will go up. Okay, in the change now, should see some washout where it comes back to the neutral position. Of course, there's turbulence involved as well. I'll change the weather now to storms building. This will cut the turbulence down by about half. Go to the motion software hold position. Okay, we're in building thunderstorms and building storms. And the motion software is re-engaged with Microsoft Flight Simulator. You can see the movements are not quite as radical as when we were actually in the thunderstorms. And now I'll switch back to active sky next. And the turbulence is set to 75% in and out of the clouds. Platform hold. Okay, we're real-time weather, active sky next. The drive's been re-engaged. So this is a typical weather over Innsbruck right now. Okay, that gives you an idea of this one segment of the motion platform. You can see how the lever's functioning. And this is pretty much the end of the initial connectivity testing. Next step will be to start putting all this in a fixture to test the actual torque and movement under full load conditions.